Cool. So after the last class that we had, which was very introductory, we are going to start with this chapter 1. And chapter 1 of this course deals basically with the basic notions that we are gonna need to explore, and we're going to use more specifically the Beer-Lambert's law and discover a little about this. As we said last time, if you remember, that the entire procedure that governs the way we actually probe matter and explore it is through an interaction between a light beam, which we use as a interrogator. We send it to the material and we collect whatever goes out of it. And there's a different sort of things that goes out of a sample, and we are going to see this. But the most important part of all this is to understand what is light made of and what would the light beam do to the sample when it arrives to it. This will allow us to understand and analyze what we collect after the sample, and this is extremely important to develop an understanding and draw conclusions about the sample itself. So as you all know, light is one of the most exciting things that exist in the world, at least to my sense. For me, actually, this was the main reason why I got interested very, very early into doing physics. So I studied physics intentionally because of this intrigued nature of light. As we know it right now, light has this what we call the dual nature or duality of wave particle nature. So historically speaking, very ancient Greek seemed to believe that light is made of particles. Some of them, I don't remember exactly who now, it's irrelevant now, but some of them used to believe that light comes out of the eyes and goes to a target. Ibn al-Haytham, which is in a Islamic scientist, he actually made the first book on light. It's called Al-Basariyat, and he actually did most of the things, if not everything, that we know now on the geometric optics. So the geometric optics that you study at school, and light beam and light rays, reflection, and all these things, Ibn al-Haytham started that. And I don't know if you know the anecdote, but Ibn al-Haytham he got himself into prison. Actually, not prison. He got himself into being locked down by, I think, Al-Khalifa al-Ma'mun, who asked him to build something for the Nile River that he could not build. So he pretended he's crazy and refused this, and he got locked in his place. So he got really confined in his place. And he used this confinement actually to study light. Ibn al-Haytham is the first one, the first scientist in the history of science, and this is believed even by Western scientists, to start what is known as the scientific method. So I'm a bit deriving out of the subject, but it's interesting subject, just to know that he started what is now known as the scientific method, which is based on observation, then analysis, description, and then communication of the information. Anyway, after that, Huygens talked about the wave nature of light. And the most preliminary experiment that defined definitely, that the light is a wave is the Young experiment. And you know this experiment, we talk about it all the time, especially in quantum mechanics. These two slits experiment by Young, which showed us the interference patterns. So most of the people, until very late in history, like 1905, were definitely sure that light is a wave. Even Maxwell himself, James Maxwell, he knew that light is a wave, and people knew how to measure, and they measured actually the speed of light physically. But he just discovered that this speed that people measured experimentally for light before him is actually the same as the speed of the waves that he was doing the mathematics for, which were electromagnetic waves. So he was the one, Maxwell, to make this association of knowledge to say that light is an electromagnetic wave. Imagine that without Maxwell's discovery, we are not able to do our communication right now. So you will be without remote teaching. So now we are learning this class because of Maxwell. Maxwell went out with his son one day, walking, and he's telling him, son, you are now talking to the only man in the world who knows who light, what is light. And this was correct. Now after Maxwell, comes Einstein. Einstein, he made, and he had his Nobel Prize because of this, he made the discovery, and he explained, in fact, his discovery was to explain the photoelectric effect, which determines definitely that light is made of particles. He made this assumption, this hypothesis. Light is made of particles of energy called photons with defined energy. Okay. So as we know it now, light acts as a wave and as a particle, depending on the situation where the light finds itself. Okay. So in addition to Maxwell, there is Heinrich Hertz. Heinrich Hertz, he actually used the theories of Maxwell's, and he created the communication, the radio waves. He studied the radio waves. So actually, not only because of Maxwell, but also because of Hertz that we are actually having this class. And the Hertz, the unit of frequency, which is 1 cycle per second, is named after him, Heinrich. James Clerk Maxwell is a Scottish scientist. Heinrich Hertz is obviously German. Now, we will start looking into the wave nature of light, because this is going to be useful for us, and then we can associate that into the particle nature of light. I'm sorry if you are hearing the same voices that I do, but yeah, my kids have some energy and it's still running until now. So this is just playing, by the way. Anyway.
It's okay, doctor.
Might be okay for you, but it's not okay for me. So anyway, thank you. So as an electromagnetic wave, it's just a wave, right? So a wave has, I mean, 3 characteristics, but they are all rounded to one and the same. Just get Hannah to get it, okay. The frequency, which actually defines how many times per second the wave is repeated, how many times per second it happens. And obviously out of the frequency, we have the period, right? So as you know, a complete wave starts from here. It goes like this. This is a complete wave. Time-wise, just a sec, yeah. Time-wise, the time that goes from here to here is usually a period, t in seconds, right? So it takes t seconds for a wave to do a complete cycle. And this is the period. The frequency is 1 over seconds, which is in Hertz. And the frequency is literally how many times per second. So this is the number of cycles per second. How many times per second is the frequency of the wave itself? And the translation in Arabic is actually wonderful. I like the Arabic name of frequency, which is at-taraddud. Not at-taraddud in terms of hesitation, no, at-taraddud in terms of repeatedness, if you want. Repeatedness. So repeatedness is the frequency, but it's normalized to per second. Now, wavelength, the wavelength is actually the length of the wave. So obviously it's in meter. Now, the way we define it or measure it is the distance that the wave will travel during a period. So the wavelength is really the distance that the wave will travel during a period. Obviously, this depends. This wavelength is going to depend on the speed of the wave. Now, obviously, for the light, this is c. So as you see here, actually, the relation is easy to understand and to remember. I personally always get used to be lost in this, but yeah, if you look at it like this, it might help you. The speed of light is the distance that the light travels during a period. So that's the distance. The distance that the light will travel during a period. The distance that the light travels is the wavelength, and this is the period. So the relation is easy. C equal lambda over t, and 1 over t is nu, which is the frequency. So lambda nu. You usually know nu or f, the frequency equals c over lambda. We are mostly used to say it like that. Nu equals C over lambda. Okay?
Yes.
Great. Anybody knows how the speed of light has been measured historically? No?
No, I don't remember.
Michelson and Morley experiment.
No.
بس هيدي الاكسبيرمنت اثبتوا فيها انه ما في اثار برا يعني
أوكي.
السبيس فاضي.
فكر إنه خلاص. أوكي.
Not Michelson and Morley, actually. Michelson and Morley, yes, they were not looking into measuring the speed of light. They were actually saying that if there was an ether, then the speed of light that has been measured, we should find different values in different directions if we turn.
Okay.
Yeah, they didn't. So they couldn't demonstrate that there is an ether. And by the way, James Clerk Maxwell, who made the most important discovery, I would say, one of the most important discoveries in science, physics, because imagine that we still did not know until our days that light is an electromagnetic wave. Imagine that. If you think about it, I think that that's one of the most fundamental discoveries in physics, in humanity, if you want. It's really a very important discovery, because without going into a lot of discussion in this, but I personally believe, honestly, that light is the basic thing that if anyone would arrive into a real reality, understanding of the reality and what's going on in this world, it should be related to light. Because a light photon, if we look at it like this, if you were a photon, if I was a photon, I would not feel nor the space, so either the space nor the time. Space and time for a photon are the same. A
Yes.
photon, when it gets created, the photon itself does not know how much it lives. And she cannot tell where it is. She or he, the photon. Okay?
Mhm.
So there's a very fundamental thing related to light. Anyway, Maxwell made this discovery, but at the same time, he made one of the stupidest suggestions also in the whole universe. He was the one who actually said that this electromagnetic wave that he discovered, or that he suggested, should actually travel in this ether. So the hypothesis of ether that is surrounding us everywhere actually is made by Maxwell himself. So he made at the same time the most intelligent discovery and one of the stupidest ones. And because he made this, people actually were really trying to prove this. They did not discard it immediately. And it took a lot of time to discover that, well, ether does not exist. But yeah, he did well anyway. Okay. So if you don't know how the light is measured, how the speed of light is measured, it's not going to be very relevant to our course, but it's very relevant to our knowledge. So I will send you this through videos. I will not take the time now to explain it. I will send it videos, but it's a very interesting thing to know how light is measured. One sec. Okay.
I googled it and I found that an astronomer in 1676 was the first one who measured the speed of light.
Well, we might run out of time with this Zoom thing. Okay, so we might do another session. Okay, to complete after a little bit after the 40 minutes. Yes, sorry, Hannah. Yeah. There's a Dutch astronomer. I forgot his name now. Who started this measurement?
Danish.
Yes, Danish. Yeah, from Denmark. Forgot his name now.
Honest.
Something with
Romer.
Yeah, Romer.
Yeah.
Yeah, but I will send you this, but he's not the one who measured it very high precision. The one who measured it with very high precision actually was a doctor, medical doctor from France. His name was Fuseau. The Fuseau experiment, not the fuseau that you could buy to wear and stuff, but yes, Fuseau. D'accord? And it was a very brilliant, it's very brilliant way to measure the speed of light. So it's really interesting to know how it has been done. So I will send you the videos that I have. Well, obviously this is, as you see, and this is very important information that I'm going to show right now on this slide, the electromagnetic spectrum. Now the electromagnetic spectrum, for those actually who do not know this, but light that we see is just part of a full range of waves that have the same nature, like light. So light is not only, we call it light because we can see it. It's called the visible range. So as you can see here, we have the scale of frequency. So the frequency is increasing from right to left in terms of Hertz. So second -1. So going from right to left, the frequency is getting higher. Obviously, the wavelength will get lower from right to left or get higher from left to right, because the relationship between the frequency and the wavelengths is inversely proportional. Okay. Now, if you can notice also that the energy of the wave itself gets actually higher when the frequency gets higher. Why? Because the relationship is known. The relationship is, let me just write with the right pen, E equal H nu. So if the frequency gets higher, the energy is going to get higher too. Now notice this beautiful understanding of things. Can somebody tell me why you think that when energy gets higher, the waves, the electromagnetic waves, actually do more damage? So for example, X-rays, ultraviolet, X-rays, gamma rays, these are waves at the high frequency level, so high energy levels. They have high energies. And this is why, obviously, X-ray, for example, can penetrate into the body. Okay, but why is it dangerous to the body? Why ultraviolet light or ultraviolet waves are dangerous to our skin?
Because it can cause ionization of the atoms in our skin.
Why it can do that?
Isn't because it kills living cells?
Why it kills living cells?
The lambda
enough to penetrate.
It has very
Sorry?
high energy, so
Yeah. So what it
Lambda is
does?
very little. It's almost the size of the atom.
This is not one. I mean, this is not what I'm looking for. I'm still. I mean, all you are just saying facts about it, but you're not telling me why it does these facts. Well, there will be 1 minute now, less than 1 minute. This session will stop. So I will just create another one. Okay?
Okay.
Okay.
No, wait. Remaining time, what? Oh, we have 4 minutes as a remaining
Yeah,
time.
we have 4 minutes. Yeah.
4 minutes, 4 minutes. So let me say the answer for this, and I will create another one to try to finish. Look, there's one visual thing that you can see, and one obviously more. I mean, I know that you guys know why the reason. What is the reason? I'm not testing your knowledge. I'm just trying to get you to say the right analysis side of things, at least to my sense. Well, obviously, it has more energy. That's correct. So this energy is released by the wave and is transferred to the electrons in the tissues. And these electrons could actually go out of the cells, out of the atoms that form the cells. Do you know that it's one electron out of its place in an atom? It makes a huge difference. Gold and mercury, if you look into the Mendeleev table, the difference between gold and mercury is 1 electron.
Yeah, 1 electron.
Just 1 electron. You remove 1 electron and the mercury eats gold, and you know that. You put mercury, you put gold next to mercury. The mercury, we say it eats gold. Just 1 electron difference in 1 atom. So cancer in the body, it can just be 1 electron away in an atom in a cell. 1 electron. It's one of the elementary particles in the universe. You take one of them out with an energy, and you just do a huge mutation. So yes, that's one of the reasons. Okay. Perfect. So obviously, as you know, we have the visible light, we have the ultraviolet light and the infrared light. So most of the waves that you are going to use and deal with are somewhere in the infrared or microwave range. Okay. Sometimes we also use X-rays to send X-rays to matter. Okay. So it's among these things that we're going to use. The radio waves, by the way, the radio waves are the actual radio waves that surround us. Okay. So now if you just open the radio, you will start receiving. So this means that already in the space around us, these waves are just moving. So they hit us, we don't just feel them. They have very low energy. Great. So well, this is another example, but yeah, it's just for if you want to visualize things. Well, you can just see the sizes. Okay. So when we talk about ultraviolet light, visible light, infrared light, X-rays, you see that the size of the wavelength, so the length of the wave, as I think Hannah was saying one time in the answer before, the size of the wave is comparable, is of the same size as molecules and atoms for
Or
the
atoms.
X-rays. Okay,
Yes.
what does that mean? This means that if I draw it like this, you know that the Young's experiment, this is the Young's slits. So this is a slit in one of the Young's experiments. And when the light was being sent as a wave, so it created, if you want, this waves from each source, and then the wave from the other source. And this created interference between them. So the points where they met, they created interference. And when they arrive actually into the screen, this is a screen, they create fringes of interference. This is the Young's experiment. Young's experiment. Great. But now, why I'm saying this? Because imagine that now you actually go up. Oh. Okay. So imagine now that you have one atom. Imagine that now you have, how to draw it? Okay, let's put it like this. Imagine you have one atom. And the second atom next to it. And the third atom next to it. Atoms like this. Okay? Now, if this spacing between atoms and the size of the atom itself, if now I bring a wave, which is light, if I bring it to hit into these atoms in a crystal, for example, okay, these are H nu, so this is light, and these are atoms. Well, this means that normally this light should actually make interferences when it goes through these slits. So now the slits are just a separation between the atoms. So the more the wave is, has a higher frequency, the more its wavelength becomes small, and so the size of the wave itself becomes comparable, even sometimes smaller than the separation between atoms. And so the wave can actually go through atoms, in between atoms, and this is why it penetrates matter. Okay, so it actually penetrates matter as an X-ray. Gamma rays, they also penetrate even further in matter because they can go into even smaller sizes of separation. Great. Now comes the blackbody radiation. Anybody has heard about the blackbody radiation before? You probably heard about Kirchhoff or Kirchhoff. Kirchhoff or Kirchhoff, depends how to pronounce it. You know him for the Kirchhoff laws in electric circuits. So you have the Kirchhoff laws of currents and the Kirchhoff law of voltages. This is the same guy, but he did not just study electric circuits like it is like science nowadays now. So nowadays, most of the people will tell you, oh, this is not my specialty. I don't teach this course because this is not my specialty, or this course is my specialty, so I should teach this course and I don't teach the other one. Or why are you teaching these courses? This is not your specialty. And this is a lot of things that I hear all the time. Anyway, these guys did not used to teach or study by specialty. They just did science. So this guy did or the electric circuit laws that you know, but also he was actually studying spectroscopy, which has nothing to do with the circuits anyway. And he studied the emission of a blackbody radiation. Now, what is a blackbody radiation? A blackbody is a body that has that absorbs light.
The ability of absorption, yeah, and
yeah. But at the
absorbs
same time,
all the radiation.
yes, but at the same time, it is also the perfect emitter of light. So it is a very high absorber of light, of radiation, but also is the perfect emitter of radiation. So let's look at how this happens. A black body has an absorptivity. That's what we call. It has the possibility to absorb equals to 1. So it's like probability. So 1 is the maximum value. So it absorbs all radiation that comes into it. And it has an emissivity of 1. So it's the most efficient radiator of electromagnetic energy. Now the question is that you might be asking yourself is, come on. You say it has an absorptivity of 1, at the same time its emissivity 1. How does that happen? I mean, well, a black body would absorb perfectly all radiation that comes into it or onto it. And actually, if it's heated, then it will radiate electromagnetic radiation, emit radioelectric radiation in a perfect way. Perfect way means that the loss of radiation is minimum up to 0 or down to 0. So there's no loss of energy radiated from the black body, but it will radiate it only if heated. So if you look at this, actually, if you look at this, it's like an oven, if you want, made very black from the inside in a very efficient way. If you heat it, you see that it radiates. It becomes red, obviously, and then at higher temperatures, it starts to get whiter and whiter, right? Don't try to do this experiment at the home, okay? Please, but take the charcoal, for example. If you are now to finish this course, or maybe you are taking this course with an narghile next to you. So for those who are actually smoking an narghile right now during the course, just look into the charcoal of your narghile or of your sisters or brothers' narghile next to you. The charcoal is black, is dark black, right? When you heat it, it becomes red radiation. It's radiating actually energy and light. Huh? Okay. Mm-hmm. Yeah, this is what I meant. Obviously, you are not going to smoke a black body, but it's like an oven that you actually, when you heat, when you raise the temperature, it will start radiating. And it radiates, and you see this radiation because it has an emissivity of 1. So what you see is basically, you are seeing it because it's being radiated. because what comes to your eyes is a wave, an electromagnetic wave, and this is why you can see it. And it comes at different frequencies, and this is why you see it with different colors. Okay? When you see black, you are not seeing black actually. You can't see black. Black is when you can't see. You know, if you get my, if you get my,
Yes.
yeah. When something is black, I cannot say I'm seeing a black color. No, I just not seeing any color. So there's no electromagnetic wave arriving from a black thing to my eyes. And this is why it looks black.
Because it's absorb all
Yes.
the wavelength.
Yes. So you will look at it and it will look black, but physics speaking, there is no electromagnetic wave coming from it to your eyes. Because the way we see is that light comes out of an object, well, reflects on an object and comes to us, and it arrives to our sensor, which is the eyes, and then it goes to our brain and tells us actually, so our brain is an analyzer that measures the wavelength of this wave and then does this translation that this wavelength actually corresponds to this color. Right? This is why there's people who are daltonians. So daltonians have the deficiency by sickness or by birth. They cannot see all the colors. They see, but not all the colors. So basically, the problem is not in the wavelength, the problem is in the sensor. And sometimes it's in the analyzer. So sometimes your eye, the eye itself has a problem. So you go to the doctor, you put glasses and you try to fix your sensor. Now, the sensor could be fine. The problem is in the brain, in the analyzer. Okay? We're just a very sophisticated, extremely sophisticated instrument. We are a very sophisticated instrument, right?
Right.
And we are building instruments around us in the same way. That's all. So, yeah, what is important about the black body? What is important about it? The important thing about black body is, now, for you and me, it's a very natural thing. Yeah, okay. Now I go to Abu Mahmoud, I ask him for manouche, and I will see the same phenomenon inside his oven. So yeah, okay. But at the time of 1900 and a little before, well, this was a new way to see, to have light, different than just lighting up a candle or burning oil. And things were related together, meaning that, you know, if you look into your room now or into your house and you look into a lamp, a light bulb that is incandescent light bulb, not the LEDs or whatever, the old-fashioned ones. It's a tungsten wire, just a simple tungsten wire. It's a metallic wire to which you apply just 200 volts of potential difference. And this wire is made in a way that it has a huge amount of resistance. So you are just heating it by resistance. And it emits light. So what we all use to see during the night is the radiation emitted by a heated body.
Right.
It's actually a lot of electromagnetic waves happening because there's a lot of electrons in this wire jumping from one state to a higher one and then emitting light when they come back. Otherwise, we can't see. So one can understand why Kirchhoff, the guy that we were looking at before, why Kirchhoff actually, who was working on electricity, at the same time was working on radiation by heated objects. Okay? Because at the end of the day, yeah, this is how we see. Anyway, I'll not take longer times. It's fine, guys, that we are going slowly. I mean, we have the time, okay? So this course is extremely small. So now actually I just adjusted my schedule to be really on time, not take myself into bad management of my time. So we will go grosso modo. Now again, my computer will die. So let me finish this. When the black light emits, a black body emits light, okay? People were very interested in why the color of the light emitted by the black body gets different when the temperature is different. And this is called the blackbody radiation. Okay, give me 1 sec. Okay. Okay, sorry. So just to finish safely, I just had to put the charger. So this is known as the black body radiation. And if you want, this black body radiation, which as I said is as basic as related basically to the light bulb, it is, the black body radiation is the milestone experiment which analysis resulted in the discovery of the most important theories in science now, the quantum mechanics, the quanta basically, which led afterwards to quantum mechanics. Well, the idea is that people were trying to explain why the light of the color, or the color of the light emitted by the black body, it changes when the temperature at which the black body is heated changes. So this is the sort of graphs that are plotted here, describes the wavelength of the emitted light from a black body. This is the spectral distribution at different temperatures. Now, classical people, meaning that historically speaking, started with Stefan and then Vienne, the Vienne distribution, and Rayleigh and Jeans, all these people, they were actually trying to explain how it happens, and their explanation was based on the following. You imagine that you have, or they imagine that they have these atoms, say it's like that, and they have this bond in between them. And then when they send light to them, sorry, not light, in this case it was not light, I'm sorry. When you heat them actually, so when you, so if you heat the black body, you are heating basically these atoms or these molecules. So call that a dipole.
Okay.
So you are heating it, right? So their theory, their explanation was that this, when heated, will get more agitated. So it will actually start vibrating, start oscillating. So this is going to oscillate, according to them. This is going to oscillate. The more it's heated, it will oscillate even more. And this is why it will start emitting light at different frequencies. So the more the temperature is up, the more the frequency should go up to these oscillators. This is the idea. Huh? This is how they saw it, the oscillator. So the problem with this is that this leads actually into this relationship here. Rho is the distribution, the density or the probability of distribution. So it's this curve itself. It's actually proportional to the temperature in a way that the more you heat, the more that you will get actually higher frequencies. So if temperature goes very, very high, you will have what we called at that time, or people called at that time, the ultraviolet catastrophe, because you will have an infinitely high peak. If the temperature goes up and up, you will actually things will start radiating infinitely into the ultraviolet. And this was a catastrophe. And obviously it does not describe what happens in reality. So in this case, we had an experiment. People can just heat a black body and they can do the experiments. It's reality now. They are just trying to explain it correctly, and they couldn't. This expression here, this one, of Rayleigh and Jeans, if you just put it mathematically and to try to draw it, to plot it on any software, it will not give you this shape, at least not for high temperatures. It will give you maybe at low temperatures, but when the temperatures get high, it will get very high up like this. It does not actually explain experiment. So there is a problem with it. And the guy who solved that was Max Planck, okay? I will stop here because, I mean, we've done 70 minutes now, so I will have to stop. I don't want to take all your evening, neither mine. So I will stop here for the Max Planck, but just know that this experiment, the explanation of this experiment, led Max Planck to actually also do one of the most important things in universe, which is the definition of quanta.